Well, thank you everyone for still being here for the last lecture. Today it's going to be the final part of this lecture. We will finally see the major result of this lecture. That is, we can embed into a partition evolution in Brownian local time. By finding the embedding, we mean we will focus on the continuum structure, and we have already established in the previous lectures that amounts to find the following structure. That is a stable living process with only positive jumps. Maybe start at some position. Its initial position corresponds to the lifetime of the initial table, and each of this jump corresponds to the evolution of some table. And each of this table is the size of the evolution of the table is given by square Basel excursion with parameter dimension minus 2 alpha, and the living process itself is a 1 plus alpha stable living process. Right? This is the structure we want to discover in the limit. And by saying that, we implicitly always assume theta being 0, because theta positive is just some operation of the theta 0 case. Okay, this is the structure we want to finally discover in the Brownian local time. And how do we do that? So we have the playground, is the flow lines that we introduced yesterday. Let me recall what we have done. And by doing so, let me enlarge very little bit about the setup of yesterday. Yesterday, we think about the local time of the Brownian motion. But today, let's do it with a perturbed reflected Brownian motion. What does this mean? I mean the following. I assume B is a one-dimensional standard Brownian motion, so absolute value is a reflected Brownian motion, and LB0 is the local time of the Brownian motion B, or reflected Brownian motion, or the same at level 0. The same for the reflected or not. Okay, reflected Brownian motion is composed by a Poisson-Point process of Brownian excursions. And what do we do? By perturbed it, then X is called a perturbed reflected Brownian motion. So what's the difference between X and the Brownian motion is we are still using the same excursions of the Brownian motion. You realize the only difference is you are perturbed it by some linear scale of the local time of the Brownian motion. So if you are, for example, inside some excursion, this local time at level 0 will not change. So inside the excursion, locally, the behavior is exactly the same as this excursion. But you have to arrange this excursion accordingly, according to the local time. So for example, the local time scaled by mu should look like this. This is a mu times the local time. Then what is X? X is for every flat part, you just put back the excursion of your Brownian motion. Okay? So it's the same as a reflected Brownian motion locally for each excursion. You just arrange this excursion in decreasing in some way descendingly. Okay. In particular, if mu is just 1, then xt has the same law as a Brownian motion. All right. What is the advantage of this guy is all the story we developed yesterday work in the same way. I still have bicontinuous local time at level x until time t for x. Okay, let's continue. Let's consider the local time of x. I still have a bicontinuous version. I can still consider the process rho t defined exactly the same way as yesterday. This is again a space filling curve. And I still have a white noise, again defined in the same way as yesterday. Then the theorem of Edicom, Hu, and Shi. In their setup, they actually have considered this generalized setup. They show that almost surely for any A R A and R, if you consider the local time, if you consider local time at until the inverse local time tau r, here tau AR is the inverse local time. That means the smallest time such that local time at level R is larger than A. I still consider this local time. Yesterday I have an exotic notation. I call it as S R Y A. Okay, I still consider this. Then this gives you a square base outflow in the meaning that this flow, call it Y. I would rather use it R plus H. In the sense that it satisfies the stochastic differential equation. W 0. Okay, I can't remember. Yes, 0. This is S R Y S R Y A dy plus plus this parameter. This parameter, let's do it in the way 2 divided by mu below 0 and 0 above 0. So almost surely for every point you find that this flow is a strong solution. of this differential equation. So what does this flow mean? It means you start from a half-plane point A and R. A is the local time, R is the level, and you run this flow line. This is at each level you get SRY A. That's the meaning of this. And the theorem just says you still get a square Basel process, but you can now play around with mu to get different parameters. So this is a square Basel process with parameter 0 and 2 divided by mu. Okay, so that's great. We can play around with this parameter. And for today, I will always make mu equals to, well, rather 2 over mu equals to 2 alpha. Right, that's the 2 alpha we see here. That will be very useful to get this 2 alpha. And let me again emphasize this flow line. This flow line means you, at the same time, you get everything. You get every point starting from, you get every line starting from every point A and R. And you have yesterday the regularity property saying that each line is continuous, but if you variate A, you get Gedlach process, and all these lengths will merge each other the moment they coalesce. Right, and to construct the line for uncountably many, what you can do is by construct only on the rational points and use approximation. That's also what I have done yesterday. And let me say a little bit more word about how does this rho and W interact with these flows. Okay, and that's kind of two remarks. First, if you look at the boundary of rho, the boundary of rho are the boundary of the range of rho s smaller than t is just the local time at time t for level or for every level. In particular, if you take t equals to tau AR, the one we like, it means if we'll always think about the local time and the level half plane. Okay, so the time for our meaning is now it's never the real time, it's the local time. And at this time, my Brownian motion or my rho will get to the point after this exploration. I get to the point A and R. Then the boundary is just given by these guys. In particular, you're going up, you get the flow line S. But if you go down, because this flow line, remember, I only define it for h larger than 0. That means I always look at the upward direction. And the backward direction, we will get something different. That's the dual flow. Okay, let me remind you what is the dual flow. The dual, because I wanted to go backward, so to make notation clear that we're going backward, I will put a minus sign in the same meaning as this x and r, but for me, this s is evolving in the space that is going backwards, so everything is kind of negative. And this flow line is infimum b such that the flow r x b is larger than a. Okay. So remember what's the meaning? It means, okay. It means if you want to look at a dual flow starting from A at level minus x, then what you should do is you find, in order to get its value at R, what you should do is you look at every point, you look at the flows for every point starting from R, the forward flow line, to get the exact point such that to the right of this point, if you start from the right, you end up to the right of A. Start from its left, you end up to the left of A. This is the flow line by, let's say this is B prime, B, and this is the flow line S, R, and B. Okay? You find the right critical point so that flow line to its right is to the right of it, to its left is to the left of it. And the property of yesterday tells you S star is itself a flow line. S star is a square Basel 2 minus 2 alpha. Okay, 2 alpha is a 2 over mu. That's this 2 over mu. We are always at this. We are not always at this fixed parameter. This is flow, but I have to also emphasize that it's killed at 0. Because usually 2 minus 2 alpha gives you some value between 0 and 2. And square Basel process between 0 and 2 is reflecting. So it could go out from 0, but the dual flow is not. It's the version that is killed at 0. All right. That's the flow and dual flow and how they are related to this boundary of the exploration. And you also see the how does W interact with the flow is a kind of domain Markov property. Or if you want some decomposition of my flow lines, it says the following. If I want to change parameters. Okay, before I say so, if I go with a flow line Y, starting from A and R, this flow line Y, what you can see is a decomposition. You look at the region here, and of course, W could be restricted to this region, and this region, W plus, is again a white noise. If you say you make everything minus Y, and this white noise is independent everything to its left. And I haven't precise what is Y. Let's do it the following way. I think for the moment we need to introduce another important point of view. That is, okay, the theorem tells you if you look at the local time, then it satisfies this solution of this strong Markov, strong solution of this SDE. But nothing prevents you to change this parameter. You can use any delta to solve this system of SDE and to build this flow. That is to say, and they are all driven by the same W. So what we'll do is I will consider all square Basel flows driven by the same white noise. In particular, if you choose this parameter correctly, then you will recover the local time because of the Rhineland theorem. But at the same time, we also know all the information of all other different parameters flow lines. And this is very crucial because we are going to play with these different parameters. So back to this picture, we want to see how the flows are decomposed according to a different part of this white noise. So say Y is a square Basel delta 1 flow. I think what is best is the best way to present here is I make Y absorb at really some time theta. Okay, let's say Y is a square Basel delta 1 flow, and I look at the right-hand side about this square Basel delta 2 flow, the orange flow. Then what you will realize is S minus Y, you know what I mean? It means the difference between this part will be a square Basel delta 2 minus delta 1 flow, but you change the parameter at the level theta. Because above this level, you are only deleting by 0. The parameter will not change. But below this level, you are kind of deleting some part, which is a square Basel delta 1. And because of the additivity property, we know delta 1 plus delta 2 minus delta 1, you get delta 2. And W plus, and this flow is completely driven by W plus, independent of everything to the left of Y. Okay? So in this way, you kind of decompose this orange flow into two parts. One part is square Basel delta 1, one part is square Basel delta 1 minus delta 2 minus delta 1. And these two parts are independent. That's a useful observation. And you see this kind of a domain Markov property by, it could be, this is a fixed time. It could be used in this dynamical version by this, to apply it with the region that you discovered by rho. You find that after some time, T, the region you discovered by rho is independent of everything else. And everything else, again, has some proper white noise there. Then you get some regenerative property, you get some self-similarity, you get some independence and stationary property. That's how we finally could discover the Levy process. Nice. Okay, back to the picture. We want to discover this picture in the flow line pictures. So I think maybe the easiest way, the first question we can think about is question 1 is how to discover, like yesterday, we have described the first table evolution together with everything else evolution. That's the yesterday the interpartition evolution. We have an interpretation of interpartition evolution in the way that we separate the contribution of the first table and the other tables, and we see that this purple line is a square Basel 0, right? That's the total mass of the interpartition evolution when theta is 0. And apart from, if you have only one initial table, then the initial table will give a contribution of square Basel minus 2 alpha until its lifetime. The other new tables, you can imagine these other new tables are given by those excursions. So inside of it, you actually see many, many excursions they put together, give you a contribution of square base cell to alpha until the lifetime of the first one, the first table. And then you continue with the square base cell 0. Okay, I think with this picture, you see some similarity with the flow lines. Okay, so how do I discover this picture? I can just start with my flow line. I start with the size of initial table. I run a flow line y that has parameter square base cell minus 2 alpha. Okay, that's something we can do. You see, in the purple remark, we say, actually, we know every flow line, every parameter from the same, driven by the same W. All right, and at the same point, you can also run, okay, I think you can, this is, I think for further use, it's better that I draw it in blue. At the same time, you can also draw a red line, something like that. This red line, okay, blue line is square base cell minus 2 alpha. Red line is square base cell 0. They are all the flow lines that they can obtain from this SD with the same white noise. And then what you get is the size of the first table and the size of the total mass. So what's the difference from this simple picture and the real interpretation we want is we want further decomposition of this area. Okay, that's the following task of this lecture. So why do I draw it this way? Because we know the difference of these two flow lines according to the decomposition. What's their difference? That's a square base cell 2 alpha, independent of the blue area. And you know square base cell 2 alpha is itself reflecting at 0, so you should touch 0 at some point. Well, that's also a nice observation to say, okay, that's a property of interpartition evolution I didn't mention yesterday, is you always have some exceptional point when, exceptional time when you have a single table. Okay, that's the exceptional time. You look at this time t1 at this time, because this, the difference is square base cell 2 alpha, it could touch 0. So whenever this process touches 0, it only remains the leftmost table. So you have only a single table in the process. But this is not the case if you put a fixed time t, that you don't get it. If you put a fixed time t, the theory, what we know is you have a first table, and the law of the following table is always a p-dip Poisson-Dirichlet interpartition alpha alpha with some rescaling rescaled by its total mass. So in particular, you have infinitely many of tables at any fixed time. Okay? At a typical time t, you have infinitely many tables, but you're always able to discover some exceptional time with only one table. That's a funny fact about the interpartition evolution. Okay, this is what we want to do in the next part. So, and you see what you really need to do is to look at two flow lines with two different parameters. So this is the philosophy, and now I can explain our main results. Oh, sorry, I removed this SDE, but you know it's the meaning. So there is a theorem. To get the theorem, we have to introduce two flow lines. This is the blue flow line. They have parameter separate from 0, minus 2 alpha below, no, 0 below, and minus 2 alpha above 0. And you also have the right flow line given by the actual local time flow line. Then you know it's really driven by the same white noise, but the parameter is 2 alpha and 0. The difference is the blue flow line is always has a smaller parameter than the red flow line. Observation is almost surely blue is always smaller than red because they are driven by the same white noise. If you look at the SDE, the drift parameter of R is always larger than blue, so it's always to its right. It's always larger. So typically, if you start from a fixed point, A and R, what you can realize is some blue flow and the red flow. They can touch back each other because the difference is 2 alpha, and the 2 alpha is reflecting. Okay, I think let's continue. I should be able to present the result in 15 minutes, then we can have a break and recover with the proof. Okay, this is always the case. The blue is to the left of the right. And the difference is square base cell 2 alpha. Well, that's not exactly what we want because the right parameter, the excursions, we want to build the tables. That's minus 12. To get minus 12, you kind of want to make blue to the right of red. Then blue minus red get to minus 2 alpha. But this is not going to happen. So what shall we do? We consider the bifurcation point. Remember what is a bifurcation? The bifurcation is some point when you have a red flow. Let's say it's A and R. This is the red flow line. R, A. This is the leftmost, the left limit version. So it's not the actual flow line starting from this point, but you are rather looking at some point before A. You start some point before A, you will eventually merge with this leftmost version of this flow line. And you make A prime tending to A, you will get a limit of configuration limit line look like this. This is the bifurcation. And why this bifurcation happened? It corresponds to, if you go back to the picture, I need a larger picture. If you go back to the picture of the process X, because I should not write S, it's always R, the red one. So let me recall how the bifurcation appear. The bifurcation appear because of the excursion of your process X. Let's look at R. You find that, for example, here you have a large excursion, and you look at the point before and after, say, this point before and after both have a contribution of, okay, this is tau AR. This is the first time, that means this is the inverse time, inverse local time of level R when you reach amount of A. After this, you will immediately get more local time than A. But this is the end of the excursion. You can go back to the starting point of the excursion. This is tau AR minus. And then you look at the local time picture. You find that here you will start from A and R. You got the flow line. you get the left version of the flow line being different from it because of the contribution of this excursion. Okay, this amount is just the excursion of this local time, and you know, this amount is a contribution of local time of this excursion. You know, it is a square base of 0 excursion. All right, that's still not quite what we want. It's a 0 excursion, we want minus 2 alpha. So what shall we do? You look at the bifurcation of red, then you realize what is the blue? Blue is to the left of this line. But it may happen that the blue are A minus and blue A is also bifurcation. So if we are in a very exceptional point, that is, if AR is both bifurcation point for blue and red, then you find some blue line starting say, with the same point to the right of a red line. And the difference, morally, the contribution is minus 2 alpha. And this is the idea. Let me give the definition of this, a formal definition of this little area. I define TAR. This could be defined for any AR in the plane. I define TAR to be the region the region, the shadow region in between because this will eventually they will touch back each other. Oops, sorry. Such that R the left version of left limit version of the red line, it's smaller or equal to B, but strictly smaller than the blue line. I call it TAR. So in theory, we can define this TAR region for every point, but most of the points is just empty, unless AR is double bifurcation point. In that case, it's not empty, and by our definition, what is TAR? TAR will include the left boundary, but not include the blue boundary. I also not include the top and the bottom. Okay, that's it clear. Now I can present our main result. Okay, a little lemma. I will prove lemma later. So for any AR and A prime R prime, either TAR intersect TAR is empty, or one is completely included in the other, or vice versa, or this. Okay, because of this lemma, we can find the maximum TAR which is the maximum for inclusion And this thing gives a partition of the half plane. Okay, we can maybe give a name of this region. We call it spindle, so that it's so that the terminology is consistent with this spindle and the scaffolding construction. You can also think about it as a bubble. You know, each bubble, they either disjoint or one is included in the other. So you can consider all these maximum bubbles. They're maximum for inclusion. And if this bubble is maximum, if you look at another bubble, either it's inside of it or they are completely disjoint. Okay, so that means the area, this region, and this, if you consider all these maximum bubbles, you get what you get is a partition of the space. Okay, I cannot draw the entire picture, but you can imagine it's covered by all of these bubbles. And each bubble gives a contribution, but you can think about it. You give a partition of the space except of this boundary point. You have a partition and given by all this open small region and a cascade given by the boundary. Okay, now is to compare this picture with the Marked-Levy process picture. So what should we do to get back to this Marked-Levy process is, okay, there all the bubbles are connecting to each other in a different order on this plan, but here you have a clear way of order of bubbles. They are all ordered from left to right. That means we should develop a way to explore all these bubbles to give them an order. Then how do we give them an order? It's given by the rho. Let's take exploration order of rho. The main result is like this. Take exploration order of rho, we get Levy process marked by square Basel excursions. Okay, again, it's an informal way to present our result. It's saying because we have exploration order, we are exploration the space according to the time, then by the order of first exploration or the second exploration, so who is explored by which bubble is explored earlier by this rho will be put to the left, which bubble is explored later by this rho will be put to the right. Then we get the right order. And this only gives you the good order, but you don't get the Levy process yet. So why is this? If you think about a Brownian motion, a reflected Brownian motion, this is very simple. You just using the Euro exploration order, you discover one excursion after the other. But if you use the actual time t that you see the next excursion, you don't get a Poisson-Point process. What you need to do is here you define, this is analog. You define local time at level 0, if you call it L, and consider inverse local time gives time change. Then the excursion you discovered at this inverse local time is a Poisson-Point process. Okay, then you get the good Poisson structure, good independence way. This is what you know from the Brownian motion. Here is the same. You have the exploration give you the right thing, the right order, but it's not yet giving you the marked Levy process. You don't have a Levy. You don't have a Poisson point process of square base cell excursions. What you need to do is define a proper local time and find the inverse local time as a time change. Okay, this is what's going to be the final part of this proof and this lecture. So let's have a break and continue with this final part. Continue the final bits of this lecture with the proof of the lemma and the proof of the theorem. I find the proof is very funny because we are only going to prove it by pictures. We don't use the Euro way to work with analysis, work with the Ito formula. You see nothing behind the picture. You just use the apparent reality of this flow line, you get the proof. And we are going, there are several properties, but the properties we are going to use most likely is just just two property. One, blue is smaller than red. So just the principle. And the other is the coalescing principle. Okay, if you are in the same parameter, once they touch each other, they merge, they coalesce and continue. Okay, just by these two principles, we can more or less prove the lemma and the theorem. Of course, lots of things behind there, but the principle gave you a good idea. Okay, proof of lemma. Let's show that they are either disjoint or one included the other. Let's put two, let's first put a table TAR saying without loss of generality, let's say R prime is larger than R, and see where is the other table. We have several possibilities, either is to the right of it, or to the left of it, or inside it. We see that in either case, you cannot get a bubble that intersects with this. Why? So what is a bubble? If the other bubble is trivial, there is nothing to prove. Let's suppose the other bubble is not trivial. Not trivial means it's another, again, itself, a double bifurcation point. You have a red flow starting from this other point, A R prime, and a blue flow starting here. And you know we have the coalescing principle. This blue flow is going upwards. Finally, it will touch a point on the blue. Not to the right, because the blue is to the right of the flow, okay? And once you touch it, you will follow the same line. And for the left part, the same. Once you touch the boundary, you follow the same line. That means the bubble created by this A prime R prime is totally inside of it. Okay, that's one of the cases we are allowed. We just do not allow intersect, but this is inside of it. Okay, similar thing happened to this. Suppose the red flow line will touch the blue one at some point, and then you can continue. How do you continue? You cannot go inside. Okay, this is not allowed, because if you think about this point, the flow line starting from this point, what are they? Because of the flow property, once you are getting this point, to draw a flow line starting from, a blue line starting from this point is the same as a continuation of this guy. So the blue line starting from this point is just this, and the red line, as we said, it has to be to the right of the blue line. Okay, so that means if this is the boundary of this table, of the A prime R prime table. The left boundary can never go inside this TAR. So they cannot intersect. The right boundary has to be something here, because the left boundary can never go inside. They cannot intersect each other. Okay, this is done. The other side is the same. Okay, very simple principle, and we proved the lemma. Now, to get the theorem is slightly more complicated because we need to define some local time. And I can give you the answer. The local time is going to be at the blue boundary of tables of the blue boundaries of my exploration process. This is the local time. This is the correct local time. Why is this? Then I should give you the proposition, that is how you explore a bubble, a table, or exploring such structure by rho. What will happen? How do we explore this guy? The first thing is, okay, let's say this bubble is here in the picture, and rho is exploring the plane. And what is the first time I get inside of it? And the first thing is, you may touch the left boundary at some point, but then you will not go inside. The time you really go inside is always from the bottom. Okay, that's the first property. That is, rho will enter. Okay, let's call it T. Rho will enter T at the bottom. Proof. Okay, what is its bottom point? Let's put it larger. You know, the bottom point is a double bifurcation point. So it's also a bifurcation point of my red flow. And what is the bifurcation point of the red flow? It is excursion of x. Then how is the local time flow explore the excursion of x? It means, okay, this rho t is running with the actual time. So for this excursion, have you first get this time t1, and then get this time t between, and finally get this point t2. So then where is my local time exploration point at this time t1? Well, all this excursion here corresponds to the contribution of local time of excursions. So I haven't discovered, at time t1, I haven't discovered any of them. I know nothing about what is inside the red bubble. So AMSS is at the bottom. This is done. And then, okay, you know, after this time, rho will gradually explore this bubble, explore this red bubble, because continuation with time t, you are on this excursion. On this excursion means you will gradually explore the contribution of local time of this excursion until the last time, t2, you get back to the bottom point again, then you can go to somewhere else. Okay, that's what happens to the red bubble. But what you really want to know is, how do you discover the blue bubble? Okay, the second point is rho t after entrance will leave t at the first time from the top. Top is this point. This point. This is top. Top of the bubble. Okay. Then why this happens? Again, proof by a picture. Proof. Yes. Let's recall that the boundary of rho, what is it? It's always rho L T something. It's always a local time line at this local time that the exploration boundary of my rho is always the local time at time t. In particular, if I put t to be some heating time, and this is more or less the upper part is more or less the blue flow, the red flow. Sorry, the red flow. This is the property we are going to use. Suppose that we are in the following situation. I'm exploring Bx for the first time. Okay, suppose that I get Bx. Suppose that rho t gets to Bx. Okay, then what is going to be the boundary of the exploration? The boundary of exploration is at Bx, you are going to make the red flow. And suppose that Bx is outside the line, you can always look at the same vertical level, what is the corresponding point as the blue boundary. This is what you always can do. Suppose that Bx is outside the blue boundary. You know, if I draw a red line from the blue boundary, because of the comparison principle, it's always to the right of the blue. And you start from something even to its right. Because of the correlation property, you have to happen is either, okay, you go outside, never touch it, or you touch it and then merge with it, continue with it. Okay, and whatever it is, either this guy or this guy will be the exploration boundary of your rho. That means the time of you touch this Bx point, you must have explored everything here, including the top point. This is the proof. Okay? Whenever you touch something outside it, it means you have already explored the top point. That means the top point is the first time you leave it. Third property. Okay, let's now summarize what we have seen. We know this rho will enter from the bottom. He will explore part of it and leave at the bottom. And you know, you will eventually finish this exploration point. You will eventually completely cover this table of this bubble when you finish the completing exploring the right bubble, which will happen after you get to the time of the end of the excursion. All right, and the next question is, okay, you know you leave the bubble at this point, and how do you discover the right part? The answer is, I will, so say I touch the right part, I go from outside to the right part, to the blue boundary at some point, let's say at some type T1. Is the time you go back and go back to the blue boundary. And the property is at time T1, Rho has completely discovered or explored the blue boundary above the hitting point. Let's say this point is Bx. The blue boundary above X has completed the discovery of this X. And you will go inside, explore some region inside it, and leave the bubble again from the same point. Then Rho explores some part, a little droplets, a little bubble inside the table, and leave the table at the entrance point. Yes. Again, the proof is by picture. Okay, suppose it's quite similar proof as at the second part. Suppose that my rho is at this point, at the entrance point, then what is the boundary of rho? The boundary of rho gives you a contribution of the red flow line to its upper point. And you know the boundary of rho is the place you have already discovered. And because the boundary of exploration at T1 will be given by the red flow line. Red flow line is to the right of blue flow line. That means to the left of this red flow line, everything has been discovered. This gives you the first statement. Okay? And second statement about how you leave this area. So let's say you leave this area at some point here, not the original point. Then again, what is the boundary of exploration? It's again something completely cover everything. It means you must have complete something not only inside the table, but also something between it, between the red line and the blue line. That means you must have already been somewhere outside. So this is awkward, which means you can only live for the first living time when you're exploring the bubble has to be, first living position has to be the entrance position. Because if you live outside, it means either you have already discovered something outside which contradicts to the definition of the first living time, or it means the blue flow line starting from this point coincide with the red flow line, which is also awkward. And the second part is done. All right, then let's go back to our definition. Suppose we have a way to define the local time, and what will happen by this inverse local time. And I call eta inverse local time I mean, local time means the blue boundary local time. blue boundary rho local time. I have inverse local time. And this is the correct time change. I will look at this process. What is this process? Inverse local time means, or the local time means you are only, the time is only increasing at the blue boundary and not increasing at anywhere else. So it means and look back to what happens is all the time I spend inside of it doesn't count at all after my time change. So it means immediately you get to the bottom of any table, you will jump to the top of the table because all the exploration before the first time you leave the table doesn't count at all. We skip the time and immediately get to the top position. Okay, that's a rule. And on the blue boundary, you are spending times, then it feels like you are descending with the blue boundary. Yes, because that's how we discover it. You know, we discover, the first time I discover this point, it means I have already discovered everything above it. It means when you discover the blue boundary, you are discovering it in a strictly decreasing order, in a strictly descending order. Then you go back to our picture before, it feels like you are descending gradually, linearly, when you were discovering a blue boundary until every time you see a new bubble. That means here. Because how you discover the blue boundary, if you discover something inside, then you go outside. Go outside, you see some new bubbles. You see some new bubbles here. And every time you see a new bubble, boom, you jump to its top. And then discover a blue boundary gradually. When you see a new bubble, boom, jump to its top. So this picture looks exactly the same picture as we have done to make a contour function for the discrete tables in the Poisson-Point process. And in the end, you get, of course, Levy process, a stable 1 plus alpha. In more or less the same idea as the contour process of our tables in the discrete. And what is the jump of it? Each jump corresponds to a bubble or a table, or we call it a spindle. I have some different names of it. And the size of the jump equals to the height of my spindle. Okay, again, we are in the very much similar setup as before. And what is the area of a spindle? It is blue minus red. And this spindle is height of this table. And the width of the table is exactly given by a square base L minus 12 excursion. Of course, there are pages of proofs behind it, but you see the moral is here. All right. Yes, this gave me the structure of a Levy process embedded with excursions embedded on it, and here we are with these bubbles embedded on it, and the proof is done. Okay, in the final 10 minutes, let me give you some interpretation of the proof and some other remarks. This is the X is our Brownian motion with time change, you get the Levy process. Well, if you look at the exploration process with time change, the same time change, this exploration process lives in the plane. And what is meaning of this time change is you only spend time on the blue boundary. Everything inside the bubble doesn't count. And what is remains is you get the gasket of the partition. Okay, it means we eat up everything inside the spindle, inside the bubble. We really keep the boundary of the bubbles. And this casket is a shredded sphere, a shredded plane is a plane version of shredded sphere of this group of people, B and Korean and some other name, I can't remember. Why is this? Because in their paper, it's saying it's encoded by this Levy process, encoded by this Levy process Xi. Essentially, it's saying you make a quotient space of the interval 0 and 1. The rule is 2 times T1 and T2 are corresponding to each other, equivalent to each other, if and only if no jump separates them. It means you look at the value of this Levy process. Here you see a jump blocking them, then they are not corresponding to each other. Or if you see something's here and something here. If there's no jump between them, the jump is either all above them or all below them, then they correspond to each other. And well, why they are the same? It's also more or less the same thing. We separate 2 points if there's a jump between them. That's why they have the same structure. And remark 3 is why do we feel this is a nicer structure than just knowing the marked Levy process is we have some self-similar structure inside of it. You can further go inside each bubble. Inside of it, inside, you still have some independent white noise, independent of everything outside. And with this white noise, you can again construct flows inside it. So you have an infinitely nested structure, infinitely hierarchical structure. And back to the tree evolution we want. What was the intuitive idea of this bubble? It corresponds to one subtree on the spine. This evolution of one subtree on the spine. Then we said that in order to complete the tree construction, the tree diffusion, you have to further decompose this subtree. And here, automatically, you have a structure inside the subtree. That means we can encode the whole tree diffusion by exactly the picture of this, all these flow lines, all at once, at the same time, for every level. And everything of this is just measurable with respect to one single Brownian path. I find it's a very beautiful construction, but of course, we haven't yet finished this part. This is an ongoing project. We want to explain the tree diffusion by flows, and naturally, because we have a nested structure, we have hierarchical structure. We can get inside of each subtree and inside of each of the sub-subtree all at once. I find it's a good advantage. And another thing I'm not familiar with, but at least Elie Edicom find some similarity with Duplantier, I think Miller, Sheffield. Okay, forgive me. I'm just saying something nonsense, but I'm copying what's said by Elie Edicom. He says, in their picture, in their Asterix long monograph, you find some SLE exploring Gaussian free field. In the end, this Gaussian free field is encoded by two Brownian motion. In the end, it also constructs some area by some crossing Levy process. So you gain some meteorological or flavor analogy of our process. Our process is the row process exploring a white noise. They are SLE exploring GFF. So you feel there's something similarity. Maybe you can get some connection, or at least you can try to use some of the methodology developed by them and a continuation of their a lot of work continuing with this setup. You can see a lot of similarity there. And in particular, SLE kappa, when kappa goes to infinity, scaling limit is just a real process. That is something discovered by Vincent Befaha in his PhD series. So you see some beautiful analogy. Okay, this is I think I will stop here. Summarizing, we have a discrete Chinese restaurant process. We got the limit, which is a Levy process marked by excursions, and then we use crossing bifurcations of the blue and red flows to get this. And there are many applications, maybe final application. With this new construction, we can complete a conjecture that haven't been proved before. That is, the total mass of beta is independent of the normalized version. This is how this is what we proved, which is a conjecture before. But we can prove it by using this new construction, which couldn't be proved without this correspondence to this Brownian motion. Okay, thank you.